Welcome! Today, we're going to get our hands dirty with some really beautiful geometric machinery. We're looking at one single powerful equation that solves a really tricky problem. How do you get the geometry of two different surfaces to talk to each other, especially when one is folded or branched over the other? We're going to break this thing down piece by piece.
Okay, so here it is, the Ramification Compatibility Condition, or the RCC for short. Now, I know what you're thinking, that looks intense, but I want you to think of it less like a formula you have to memorize and more like a perfectly balanced story. On one side of the equation, you've got this smooth, totally well-behaved geometric object. And on the other side, you've got a collection of pieces that, on their own, seem kind of chaotic and singular. So our whole mission today is to figure out how they can possibly be equal.
So here's our plan of attack. We're going to break it down logically. First, we'll get a handle on the problem this whole equation is meant to solve. Then, we'll look at each side of that equal sign all by itself. And finally, we'll see the real magic that happens when they come together. So, let's dive in.
So what is the big picture here? Well, imagine you're laying down the fundamental laws for a brand new universe. This equation is exactly that. It's a fundamental law, but for a universe of what are called spin-Kähler curves. These are surfaces that come with extra geometric structure. And this equation, it dictates exactly how maps or morphisms between these surfaces are allowed to behave. It literally sets the rules of the game.
You can really think of this as the theory's superglue. It's the thing that makes sure all the geometric rules hold up, especially when things get complicated. And that complication is called ramification. It's what happens when a map isn't just a simple, smooth covering, but instead it has points where the surface kind of folds back on itself. You know, like the branch point on a tree root.
All right, let's start on the left side of the equal sign. This part of the equation is all about how geometric information gets carried from a target surface back to our source surface.
You know, this entire chunk on the left-hand side, it really just describes one single idea. Imagine our source surface X is looking at another surface, Y, but it's looking through a special kind of lens, and that lens is our map F. This whole term represents the complete geometric picture, the spinorial connection, that X sees. It's the geometry of Y, but seen from the perspective of X.
And here is a really critical clue. This view that X has of Y is perfectly smooth. It's totally continuous, even right over those tricky branch points. Now you got to keep that in mind, because it sets up this fantastic puzzle. How can this perfectly behaved object on the left be equal to the right-hand side, which, as we're about to see, is built from parts that individually kind of break?
Okay, time to hop over the equals sign. Now we're looking at the story from the source curve's own point of view, its own intrinsic geometry. So the right-hand side kicks off with these two pieces. The first part is built from the source curve's own internal geometry, its spin connection, but it's paired up with a brand new object, something called a twist bundle. And yeah, just as the name suggests, this is where things start to get a little bit twisted. It's the first time we really see the effects of that ramification.
So what on earth is this twist bundle, Elf? Well, like the slide says, it's measuring a discrepancy, but a simpler way to think about it is this. It's a way of measuring exactly how much the geometry has to twist and turn at those branch points to make the view from the source line up with the view of the target. It's a precise measurement of the geometric mismatch that's caused by the ramification.
And here it is. This is the first broken piece of our puzzle on the right-hand side. The very existence of this twist bundle means that at every single branch point, its connection develops a singularity, a point where the math, well, it goes haywire, kind of like a division by zero. Now, it's a very specific, well-understood type of breakdown, a logarithmic singularity, but it's a breakdown all the same.
Okay, on to the final term on the right-hand side. This is the piece that helps reconcile how the two different surfaces measure distance.
Now, this last little piece is the conformal correction term. It might look small and unassuming, but let me tell you, it is the absolute key to making this entire equation balance out perfectly.
So this term is built from something called the conformal factor, which we're calling lambda f. You can think of it as a scaling function. It tells you exactly how much the map F is stretching or shrinking distances as it projects the target geometry onto the source. And the most important thing to know about it is right there on the slide. This factor goes to 0 precisely at those ramification points right where the map folds over.
So because that lambda f factor hits 0 at the branch points, taking its logarithm, well, that creates another singularity. So now we've got two completely different terms on the right-hand side, and both of them break down at the exact same spots. And this brings us to the core analytic insight, the most beautiful part of this whole story. This brings us to the most elegant part of the whole formalism. This is where the mathematical magic really happens.
Right? This is the central question that the RCC was built to answer, and the solution is just beautiful. It's a perfect balancing act.
And this slide just illustrates the mechanism so brilliantly. If we zoom way in on a single one of these ramification points, the map behaves like a pretty simple function. Z goes to Z to the K. And what happens is, the singularity that comes from that twist connection is exactly equal in size but opposite in sign to the singularity from the conformal correction. One's positive, the other is negative, you add them together, and poof, they completely cancel each other out, leaving behind nothing. Just smoothness.
And this is absolutely not a coincidence. This is the fundamental analytic engine that makes the whole theory go. The two singularities are literally destined to cancel each other out, and that guarantees that the right-hand side of our equation is every bit as smooth as the left-hand side. So what's the big takeaway from all of this? I mean, why go through all this trouble to build such an intricate piece of mathematics?
Well, the ramification compatibility condition is really the bedrock of this entire theory. It's what allows us to treat these branch points, these ramifications, not as some messy problem we need to avoid, but as a structured, predictable part of a brand new geometric world. It defines the rules of engagement, it unifies all the key geometric players into one equation, and it guarantees that the whole system just works.
Ultimately, the RCC takes what could have been a geometric breakdown and transforms it into a source of new, richer structure. It shows us that branching introduces this very subtle twisting effect, and that effect is governed by this beautiful, precise balancing act of cancellation. It really leaves us with a provocative question: what other hidden structures in mathematics and physics might be secretly governed by similar, elegant cancellations, just waiting for us to discover them?
This explainer was based on the monograph Caylarian Curves and One-Dimensional Complex Geometry, Volume 1 by Mohammed Ben Ammar Traidi. If you want to dive deeper into the mathematics, you can find the full work using the DOI you see on your screen. Thank you for exploring this fascinating equation with us.